Section 4.2, Direct Proof and Counterexample Part 2, Writing Advice. One thing to know before we begin this section, when it comes time for tests for this class, you will not have to write any proofs all out. The way the proofs there will work is they might be fill in the blank, they might be proofs where you have to have the all the steps in the right order, but there are not going to be any questions where you have to write the proof out in its entirety. So let's start with writing proofs for universal statements. Now again, a lot of these things are just, guides to kind of help you get started, get finished. Some of these are a little bit harder when we've got a computer, as we do, but this is all still very good advice. I'm going to skim through this. Again, we're not going to worry too much about the grammar because on tests you won't be writing it out longhand. But we do always want to make sure readers can follow our proofs, so we often put in little words just to kind of help people follow along as we go through. We want to make sure that our steps are all justified, that we haven't done something that we're not allowed to do. So it's either a given, it's something we have a definition, maybe we're pulling a theorem that we've already looked at. There's a lot of places this could come from. Again, more little words just to kind of help readers follow along and see what we're doing. We might also make little side comments in case something's not clear, or to recall, for example, if it's been a while since we last mentioned that for a particularly long proof. And of course, any equations or inequalities, we do want to see them, and we do want to see the steps that we might have to use to simplify or solve any of them. Alright, let's talk about some variation among proofs. We always tell people every proof is different. You'll see my proofs here, you'll see some of our textbook authors' proofs. They're going to look a little bit different, and that's okay. We're still hitting the stuff we need to. They don't have to be identical. Let's hit some common mistakes. One common mistake that we're going to start with is arguing from examples. I always tell students, if you have no idea where to start, it can help to work a couple examples just to see the math behind it, maybe try to find a pattern in what's going on, but an example is not going to be enough for a universal proof. So if we were trying to prove that the sum of two integers is even, if I pick two evens and show that those work, okay, it worked for those two, but that is not enough to show that it works for every even integer. So again, it's not bad to do examples. Examples are there to help us, but that's not enough to actually do the proof. Another common mistake is using the same letter to use two different things. I talked about this in our last section. If I have two variables m and n, and here you'll notice I'm using my odd definition, and for both of them we've used k. If we do that though, that means m and n are equal, and that becomes a different proof. So if you have different variables and you need to define them, in each of those definitions we also need different letters, different variables. So again, these are things that are common mistakes, and we want to be very careful to avoid them. Next thing is jumping to a conclusion. So my example for this, suppose m and m are even integers. We've got our definition, m is 2r, n is 2s for some integers r and s. Then m plus n is 2r plus 2s, so it's even. We've got a little bit more going on in this proof, but we have definitely jumped the gun here. We do not actually have a statement yet that shows this m plus n is in fact even. And again, this is a very common mistake. I don't have enough detail. I have jumped the gun. Assuming what is to be proved. Again, this is a very common mistake, is whatever we're trying to conclude, we end up just assuming that that works. And you're not allowed to do that as well. So be very careful that your assumptions do not include the thing you're trying to prove. Some of these mistakes are a little bit less clear about what it means, but confusion between what is known and what is still to be shown. And that can be one of the questions is, okay, I know this, do I actually then know this next step, or do I have to do a little bit more work to actually show that? So in this little proof here, we are trying to show that m times n is odd, and you'll notice the very first step this author took was using that definition of odd for that product. Anytime I'm taking my conclusion and just going with it and assuming that it's, working, I'm doing something that I'm not supposed to do. And so that is why this one is not going to work. Be careful of words like any and some. They do sound very similar in English, but as far as mathematics is concerned, they are going to be different. So if I say suppose m is any odd integer, that means I can pick whatever odd I like. But if I say it's some odd integer, I'm not 100% sure if that's all of them. It might just be one or two of them. So we do want to be a little bit careful with those words. The word if is, of course, a big statement. Again, the if is my given, and that's probably the only time I'm going to use it. And especially with the word because. So here, we are already supposing it's a prime. I don't want then want to put the word if after that, because it's not an if. I've already said this is a prime number. So again, if should really only be used in my given information, unless I need to drop into cases. So here we would then say instead because or since. All right, so let's go ahead and hit another proof. Again, we talked about these assumptions that you're allowed to make before, but there's just a repeat in case you need to see them again. So we would like to prove that an odd integer minus an even integer, and what are we actually trying to show? So if a is odd and b is even, then its difference, a minus b, is odd. Again, as you'll see, there's a lot of different ways we could phrase that question. Usually we try to give you questions that are very clear so that you know exactly what it is that we are trying to prove. All right. So let's pull up a problem that has a proof or a mistake in it. So here we are trying to show that if n is an even integer, then -1 to the n is 1. So here is my proof. Suppose n is any even integer. By definition of even, n equals 2a for some integer a. Then -1 to the n equals -1 to the 2a. I'm going to use a law of exponents there to pull them apart. And then I jump to 1. My real problem here is not until the very end. We're doing not quite working out here. The main thing I would say is have the 2 on the inside, because that is what's going to get me there. Because of course -1 to the second power is +1, and that is going to be the key to this. And we are going to see that later. Alright, so we talked about that difference. I do have it here. I'm a little out of order. I apologize for that. So I've got a and b are integers where they're odd. So you'll notice I've got my definitions. And again, make sure that I'm specifying m and n are integers. So let's actually take that difference. At which point I'm going to reorder this. So I can write it as 2 times the quantity m minus n, and then my +1 on the outside. So that m minus n, which I'm calling c, is an integer, since the integers are closed under subtraction. So I can write that as 2c plus 1, which is my definition of an odd number. Again, this is going to look a little bit different than how your textbook author writes the proof. This is my proof, but you will hopefully see that all of the important steps are in both versions. All right, we've shown how to prove an existential statement. How do I show that an existential statement is false? That would mean, if we remember, the negation of an existential is a universal. So if I've said there is a positive integer n, such that n squared plus 3n plus 1 is prime, how do I show that that is false? So first, I'm going to take the negation of that statement. So I will say for all positive integers n, that quantity is not prime. And because it's universal, I can then find something that will work. And let's pull that down. Because this is now universal, I can start pulling it apart. I'm going to factor that. And I would say at this point, this is then the product of two integers. Those are both integers. That's a product. That is the definition of a composite, which means it is not prime. And that is what we are trying to prove. Now again, this is my little sum up. This is the important part. Again, you will have some questions on the homework where you will have to write proofs yourself. Do the best you can. That is to get practice. Again, on tests and quizzes, you will not have to write out any proofs. It is going to be either fill in the blank or rearranging so that you have steps in the correct order. And this is everything in section 4.2.